They have to go to this one.
Yes.
Okay, it is 4:30 now, so I guess we will begin. Okay, so welcome to the computer security seminar from Purdue University. Today's speaker is Dennis Fetterly from Microsoft, and he will speak on using statistical analysis to locate spam web pages. Hope he tells us why he wants to locate spam web pages. Okay, Dennis.
Hi. As Sam said, my name is Dennis Fetterly. I'm from Microsoft Research's Silicon Valley Lab, which is located in Mountain View, California. And I'm going to talk today about work I've been doing with Marc, Manasse, and Marc Najork on using statistical analysis to locate spam web pages. First, to motivate the rest of the discussion, I wanted to show you some example spam web pages. So in this first example, you can see that the page consists solely of hyperlinks. And the target for each one of these hyperlinks is the current URL with the anchor text appended to it. So you're creating a deep structure. And if you follow one of these links, the first link is the target of this particular piece of web spam. And the 8 links beyond that go to pages similar to the one that we just came from, creating an infinite URL space. As you can see toward the bottom of the page, there are a jumble of keywords that presumably this the author of this page believes would be likely query terms, and thus make this page likely to be returned. If you look at a slightly different example, you have what was at one time a coherent block of text that has keywords stuffed down into it, and then you have keyword link pairs at the bottom. And in a final example, you have a random series of words and then a number of links. One thing common among all of these pages is they're useless to a human surfer. They are only useful to a crawler who would actually be trying to extract the links and then follow them. So here's some definitions that I'll use in the remainder of the talk. Web spam is web pages that are designed to cause search engines to misdirect traffic from search results to the target site. And there's a few different types of web spam. There's keyword stuffing, whereas we've seen you have just a set of random keywords but no actual content in a page. There's link spam, which is a technique for fooling PageRank or other link-based ranking algorithms, where you create a large number of pages, all of which point to the target site. Or there's a game. You can try and game the search engine's ranking function by publishing many different similar pages with slight variations, hoping that at least one of them will rank highly. And it's important to note that web spam is not email spam. Instead of the target being the end user who is being exhorted to buy something, the target is a search engine where you want to increase the ranking of whatever the target site is. And sometimes deciding whether or not a page is spam is a judgment call, because it might have some small bit of useful content and then say 2,000 or 3,000 links off to useless pages. And so you have to decide whether or not that's a useful page or not. The increasing importance of search engines has given rise to an industry of search engine optimizers. These are folks who help a commercial website rank highly for queries that are relevant to that site's business. They're commonly known as SEOs. And our project is to use statistical techniques to detect web spam, or at least a reasonable fraction of it. Web spam is a problem for search engines because it pollutes the corpus. As we've seen, many sites create an infinite URL space, so you get an infinite number of pages, and your index is finite sized. More importantly, as your index gets larger, your cost per query increases as well. So you want to get rid of these junk pages and replace them with useful pages. And they distort the relevance of the results that you return because of the fluctuations in ranking that they cause. And finally, these pages all burn crawling bandwidth because they're not pages that you would actually ever want to return to a user in a result query, so you don't actually want to crawl them either. We began this investigation into web spam as a result of one of the things that we discovered while doing a study on how much web pages change week over week about 18 months ago now. And we discovered a strange anomaly in Germany where pages were 9 times as likely to undergo significant change as pages on the web as a whole. And we traced most of this anomaly down to a single IP address where the pages were changing on every single reload. In our data set, we had more than 116,000 different hosts that mapped to this one IP address and more than 1 million pages, each one of which had been randomly generated at crawl time. So these pages changed too quickly compared to pages on the web as a whole, but if you looked at the other properties of them, they looked fairly normal. They had appropriate distributions of non-markup words in them, appropriate numbers of links that had the right distribution, and they were grammatically well-formed sentences, but if you put these sentences together into paragraphs, then they didn't make sense anymore. So if we could find this site because it displayed a statistical anomaly, could we use the same sort of statistical analysis to find others? And if so, what types of anomalies should we be looking for? Our initial hypothesis was that we would expect to find spam around any metric that a search engine would use for ranking, since people would have to have some reason for spamming a search engine. Here's a list of properties that we examined. We looked at the URL itself. As we saw in the first example, if you create a deep URL tree, you would expect that a spam URL from a spam site might have more path components in it, or thus more slashes. Might also be strange because it would have extra digits or dashes. And we applied the same techniques to the hostname component of the URL itself, as well as looking at the results of performing DNS resolutions on all of the host names in our set. A metric called the host machine ratio, which uses that information, which I will define shortly. The link structure that is induced by these pages, including the in degree, or the number of pages that link to a particular page, and the out degree, or the number of links that are contained in that page. And the syntactic content, such as the number of non-markup words or the length of the content in bytes. We also looked, as I mentioned, at how fast this content evolved over time, as well as perform a clustering of near duplicate documents. And just by looking at these properties, we can identify 75% of the spam that we expect exists in our collection. So about our collection. We have 2 different data sets. The first, which I'll refer to as DS1, consists of 150 million URLs, which we downloaded each week for 11 weeks. The initial crawl was a breadth-first search crawl starting at the Yahoo homepage. And the remaining weeks were crawled exactly that same set of URLs. That crawl took place between November of 2002 and February of 2003. The second data set, or DS2, was the result of a single breadth-first search crawl starting at Yahoo, and it contained 429 million HTML pages, as well as we followed 38 million HTTP redirects. This took place between July and September of 2002. For the DS1 crawl, we retained the following information: the URL, the start time of the download, the fetch duration, the length of the document in bytes, the number of non-markup words contained in the document, and an entire document checksum, as well as a vector of 84 features which identified the text of the document, any HTTP status code or error condition that existed, and we retained the full text of 0.1% of these pages that we downloaded for future analysis. It came in handy when we wanted to determine how much spam was in this collection, because we took a random sample of 750 of these pages and determined